Okay, in the previous video, we have been talking about this balanced number, and we come to the conclusion that if this balanced number is in the range -1 + 1, it means that the tree is balanced, so there is no violations, and we are just going to return the node without any modification. But if this balanced number is greater than 1, it means that the left subtree is greater than the right subtree, so we have to make a right rotation. And if this balanced number is smaller than -1, it means that basically the right subtree is greater than the left subtree, so we have to make a left rotation to make this tree as balanced as possible. So according to this balanced number, we are able to define the 4 cases. We have been talking about the 4 cases in the theoretical section. The first case is the doubly left-heavy situation. Okay, so whenever the balance is greater than 1, so what does it mean? That it is a left-heavy situation, so the left subtree is greater than the right subtree, of course, because it is a left-heavy situation, and the data is smaller than the node.getLeftNode.getData. What does it mean? Basically, this is the case 1 in the theoretical section. So the balance is greater than 1, so it is a left-heavy situation, a left-leaning binary tree, and the data is smaller than the node getLeftNode.getData. This node is the grandparent basically, so we have inserted a node, and this node is the newly inserted node's grandparent, so the parent of the parent. And the grandparent getLeftNode.getData is basically greater than the data we have inserted. It means that this data, so the given node we have inserted, is a left child of a left child. So this is how we check whether this is the first case, because we know that it's going to be a left-heavy situation, but there may be 2 cases, whether to make a single right rotation or a single left and a single right rotation right after each other. And because the data is smaller than the node getLeftNode.getData, that's why we just have to make a single right rotation. So we just return with the right rotation on the node. This node is the grandparent. So this is the case, and basically we have the node we have inserted, this A, and the grandparent is the D. So the D's left child is the B, and basically the value of this A is smaller than the left child of the grandparent. Yeah, it is true. That's why it is the left child of the B. And we just have to make a single right rotation, as you can see. Okay, so that's all about the case 1. The case 2 is the right case. Basically, I'm just going to copy and paste it because it's going to be very similar. Ctrl-Shift-F to auto format. So this is the case 2, the right situation. This is the left situation. Okay, in this case, the balance of course is smaller than -1, because we know for certain that it's going to be a right-heavy situation, so the right subtree is going to outperform the left subtree. It is great number, it is a small number minus great number is going to be smaller than -1. So if the balance is smaller than -1, and the data is going to be greater, of course, greater than the nodes.getRightNode. So I'm going to have the getRightNode.getData. So basically it means that the node we have inserted is a right child, because the node is the grandparent. Its right child is basically the parent of the node we have inserted. Then we just have to make a left rotation on the grandparent, and the node is the grandparent. Okay, so this is the right situation, this is the left situation. Okay, and then we are going to check whether if the balance is greater than 1 and the data is greater than the node dot get left node dot get data. Basically, it is approximately the same as here, but we know that the node we have inserted is not smaller but greater. What does it mean? That it's going to be a right child. So this is the case. We know for certain that the node, this is the node basically, the grandparent. The grandparent left child is the parent of the node we have inserted because the C is the node we have inserted. But this node we have inserted is a right child, so we know that the new data is greater than its parent's value. So that's why the node's get left node get data is smaller, or from other perspective, the data is greater. So this node is a right child of the grandparent's left child. That's why we have to make 2 rotations. This is the so-called left-right heavy situation. Okay, so the balance is greater and the given node is a right child. So we just have to node dot set left child and we make a left rotation on the node dot get left child. This is how we rotate the parent to the left. So we just have to rotate the parent, this B, to the left. And the C is going to be the parent, and the parent is going to be the left child of the child basically after the rotation. And then we have to rotate the previous grandparent, because before this rotation the grandparent for the node C was the node D, so we have to rotate this D to the right. Okay, so we just have to return with the right rotation on the node. Okay, and else it's going to be the right left heavy situation. I'm just going to auto format, so it is the right left situation where the balance is smaller than -1, but the data is smaller than the node get right node get data. So basically this node we have inserted is a left child, but the root's right child is the parent of the node we have inserted. So we just have to node.set right child. We have to make a right rotation. So right rotation on the node.get right node. So get right node. Okay. And then of course we have to make a single left rotation. So left rotation on the node, as we have seen in the theoretical section. Okay, so this is the case we have been considering. This is a left child, but the parent is the right child of the root node. So we just have to right rotate this F, so the parent. Okay, and then we have to make a final left rotation on the grandparent. Okay, so that's why we rotate right and then rotate left the grandparent. And basically that's all about this settle violation method. Thanks for watching.